Okay, today we're going to introduce a new type of convergence for a sequence of functions. It's called a convergence in measure. Okay, the definition is given as follows. Suppose we have a sequence of functions denoted by fk, and we have a limit function or target function f. They are defined on a measurable set E of Rn, and it's mapping from E to R bar. Suppose all these functions and the target function are finite almost everywhere on E. Then we say that the sequence of functions fk converge to f in measure. We converge to f in measure, which we denote by fk converge to f with this mu on top of this arrow. This is the notation for convergence in measure for short. So we say that it's a convergence in measure if for any epsilon, for any positive epsilon, the limit of the measure of this set is 0. So this set is something we have seen before. For every fixed epsilon in every fixed k, this is a set of points where fk is deviated from f by at least epsilon. Okay. Previously, we denote this set as E k epsilon. So once you fix the epsilon, then you can focus on each specific fk, and this just tells you the location or it's a collection of points where the fk differs from f by at least epsilon. Okay. So this is the definition for convergence measure. So remember that this epsilon is always specified. It's arbitrary, but it's specified at the beginning. So this proof can be, or this definition can be also written in this way. For any epsilon greater than 0, I'm going to introduce or going to write out what this limit actually is. So this is equivalent to saying that for every epsilon and for every delta, so this delta is actually evaluating the measure of this set. For any epsilon greater than 0 and for any delta greater than 0, there exists a integer k such that the measure of this E k epsilon is less than delta for all k greater than or equal to capital K. Okay, so this is the equivalent definition. Okay, but the key idea is pretty simple. For any fixed epsilon, this measure of ek goes to 0. Okay, so remember that all these functions are finite everywhere. So if they deviate at those points where they are infinite, it doesn't matter because we only care if the measure of this set, the measure of the points, measure of the sets where they deviate is converging to 0. Okay, so wherever this fk and f are infinite, they don't matter because they only take a measure 0 set. Okay, so there are a sequence of important properties about the convergence in measure. And the first one is, since we have seen we take this f as the limit of fk in the as a convergence in measure. The question is, how many is it possible that the fk converges to different f? And apparently, if I have another function, I call it g, and the g and f are equal almost everywhere, then it doesn't affect here, right? If f and g are equal almost everywhere, then I replace this by g, the measure. The limit of this measure will still be 0. Okay? So that means at least I can change the value of this f at some measure 0 set. And the question is, if these are all the possible limits of this fk, and the answer is yes. So the limit of this fk is unique up to uh, the change of values at a measure zero set. Or if you have two limits of this fk, then they must be equal almost everywhere. Okay, so that's the theorem I'm going to show next. So it says that if fk converges to f in measure, and at the same time it converges to g in measure, then so let's say they are both on E. So both of these converges in measure are on E. Then f and g are equal almost everywhere on E. Okay? So in some sense, this means the function, the limit is unique in the almost everywhere sense. Okay, here's the proof. Well, so let's say that for any epsilon greater than 0, I'm going to define the set ek epsilon as euro. We just set this to the set of points where fk and f differ by at least epsilon. I'm going to define the this set fk to be the set of points where fk and gk and gx, fk and g differ by at least epsilon. And because fk converges to f and g in measure, so we know that the measure of these two sets go to 0 as k goes to infinity. Okay, this is something we know. Now, we know that fx minus gx by triangle inequality, this is less than fkx minus gx minus fx, first fx, plus fkx minus gx. So what this means is if there is a point in the set, let me write it out. Okay, I'm going to claim that sorry, this should be subset. Okay, I'm going to claim this inclusion. I'm saying that any point in this set will be in the union of these two sets. So these two sets is nothing but just this part is just ek half epsilon. This part is just fk half epsilon. So I'm claiming that the set on the left must be inside the union of these two. The reason is if I have this point x in the left set, in this set, that means this inequality holds. Okay, and I know that this part is smaller than the sum of these two. Okay, and the left is bigger than or equal to epsilon, and that means this one here, this one here, at least one of them is bigger than or equal to half epsilon, right? Otherwise, if none of them is bigger than or equal to half epsilon, that means the sum of these two is less than epsilon. That is impossible, right? So if the left is bigger than equal to epsilon, then the right, on the right, at least one of these two is bigger than half epsilon, and that means x is either in this set or in this set. Okay, and now you can see, since the left set is included in the union of the two sets, I know that their measure, the measure of the left set is going to be less than or equal to the measure of the union of the two, but it must be less than or equal to the sum of the two measures. Okay, so let me first write EK half epsilon and the FK half epsilon, and this has to be less than or equal to the measure of each one. Okay, and what I know about this right hand side is this goes to 0 as k goes to infinity. Right, for every fixed epsilon, I know this right hand side goes to 0 as k goes to infinity. On the left hand side, I know this is greater than or equal to 0, but it's independent of k, and this implies that this measure has to be equal to 0. Okay, what we showed so far is for any positive number epsilon, when I define the EK and FK in the following way, then we can show that we can use the help of these two sets with the measure going to 0. Using this fact, we can show that the measure of points, or the measure of the set of points where f and g differ at least by at least epsilon, is equal to 0. Okay, but this is still different from that f and g are equal almost everywhere. Remember, for f and g equals to f and g are equal almost everywhere, I need to show that if this is greater than 0, right? The measure of the set where this is greater than 0 is equal to 0. Well, this is not different. We are not far from the goal there, because if we can show this is true for any epsilon, I can say we can set this epsilon to be 1 over n, or any number, any sequence of number going to 0. Then, noting that the set of points where these two functions or differ can be written as the union of this countably many sets, where this x in E, the fx minus gx is greater than or equal to 1 over n. Because of this, I can show that the left-hand side has a measure. So we know the measure of the left-hand side is equal to the measure of the right-hand side. And this is just less than or equal to the sum of the individual measure of the individual set but note that this part is equal to 0, since we have shown that this set is bigger than the measure of the set is equal to 0 for any epsilon, and just taking epsilon to be 1 over n, then we show this is 0, and we're just taking the sum of zeros, and it's always 0. And it's always 0, and that is how we showed that this set has a measure 0. And this set is where the two functions disagree. And they're just saying that they only disagree in the measure 0 set. Okay? Therefore, f and g are equal almost everywhere on E. Okay, so this tells us that the limit of convergence measure is unique in the almost everywhere sense. Okay, the convergence measure is somehow weaker convergence than the convergence in almost everywhere, because we only require the measure to converge to 0. We don't really require, we don't really need to know where the convergence, where the convergence or where the deviation is. Okay, as long as the deviations have a the measure of the disagreement of the location of disagreements is going to 0. Okay, so that's why we have the following theorem. Maybe before that I show example to explain what I just said, why the convergence in measure is weaker than convergence almost everywhere. So let's take an example. Say I have this function fx. Maybe I just draw it. You can see it immediately. So say I have this function simply defined in this way. Say this is 1. Okay, so I'm just saying that my first function, so let me say this is the 1/2. Maybe it's the 1/4, 1/3. Okay, so what I'm saying that's the first function. So this, let's say this is the 1. It can be any number. Just say this is 1. Okay, so say my f1 is this function. It's just constantly 1. And just all the functions are defined over the interval 0 to 1. Okay, so the first function is just constantly 1. Okay, second function is this. It's 1 on this side, then 0. And then the next function is 0 here, but 1. So basically I'm shifting this 1, this function from this to this. And next one, I'm going to just have half the length, which is a quarter here. And next one will be just taking 1 here, otherwise zeros elsewhere. And the next one, as you can imagine, I'm going to take this, and then this. Okay, and then next one, I'm going to just take 1 over 1/8 interval, and then next one, I'm going to have this. Okay, so can you imagine that if I focus on each point, if I look at any point, say here, I always have sometimes that's taking value 1 at this point, right? Because I have this small ones progressing, and next one I will be having an even smaller length, but I always get some length covering this point, then taking value 1, and then 0. So that means if I focus on a single point, I look at the sequence of functions, I realize that the functions will always come back to 1 from time to time. Most of other times it will be just 0, but from time to time it will become 1. That means at this single point, this sequence of functions I just described do not converge. Right? Look at this point. The values are zeros, and sometimes a 1 pops up, and after that it will be a bunch of zeros, and then sometimes the 1 comes out. The 1 will always come out at this single point. So that's why the sequence functions I just described, they do not converge point-wise. Okay, if you look at any point, you will realize that this will be the case. So it does not converge point-wise. It does not converge almost everywhere. Okay, because for all the points, we don't have the convergence. However, this sequence I just described converge in measure. The reason is if you look at, well, I will claim that the measure of this sequence, or the limit of the sequence in the convergence measure sense is just 0, because you look at the individual functions, they have less and less support, right? The interval they are taking value 1 will be shorter and shorter, eventually will vanish. So when the k is large enough, maybe only a slight interval they will take value 1, and all the others are just taking value of 0. So if you measure the difference from difference between fk, like this function, and the constant 0 function, you realize that only this small interval, these two functions deviate, or the fk is deviated from f. But this area is the ek. Is the ek we just described. You can say the epsilon to be some small number, 1/2 or 0.1, something like that. But this is the only place that fk is different from f. Okay, and you can see the limit of this, the measure of this this small interval is getting close, is approaching to 0, and that means the measure of this small interval is going to 0, and that is why the sequence I just described, they do converge to 0 in measure, but it does not converge to 0 pointwise. Okay, so that's why the convergence in measure is somehow a weaker convergence, weaker type of convergence. It's weaker than convergence almost everywhere. Okay, so after you've seen this example, I can go on to a property, a relation between the convergence in measure and the convergence almost everywhere. So what I'm trying to say here is, if you know the sequence converging almost everywhere to f, and the domain is bounded, then you can claim that they also converge in measure to that same function f. Okay. So first of all, standard setup, fk and f are functions defined over E. The measure of E is finite. Oh, by the way, I shouldn't say that the E is bounded. The measure is finite, is weaker than the boundedness. So if E is bounded set, then this measure must be finite. But the measure, the E may not be bounded, but can still have finite measure. For example, you look at all the rational numbers or all the integers, they are unbounded, but their measure is just 0. Okay, so I should say this is the only required measure to be bounded. And fk, f, finite almost everywhere on E. So this is a pretty standard. Usually when we have some function that are infinite, then we don't really know any behavior there. So we only restrict ourselves to functions that are finite almost everywhere. Okay. Okay, so as we said, you have a sequence, it's defined over a set with a bounded measure, and the fk goes to f almost everywhere on E, then the fk goes to f in measure, converging f in measure on E. Okay, proof. Okay, so since we know that the fk converges to f almost everywhere, we know that it converges to f almost everywhere means that if we call the original definition, that means for any remember that for any epsilon, or I say, I'll just state that this converge to have almost everywhere means that the measure that where they do not converge, the function do not converge, is equal to 0. Okay, so that means if there exists some I such that for all the, let's say, j from 1 to infinity, for k from j to infinity of, let's see here, I would say that this is a collection of points where the function fk does not converge f. And we know that the measure of this set is 0. Okay, and this also implies that for any point epsilon greater than, for any epsilon greater than 0, the measure, I just pull out this one right because if I can show this is true for every epsilon, it's the same. Okay, it's the same as this. Okay, so let's make things, we can write things more simpler. This is just the ek epsilon we have defined before. And this inside the mu is just the upper limit of this set, right? So it's just saying that, I'm just rewriting this thing. Just the mu of the upper limit of k. Just means that this is equal to 0. Okay, remember that the E has a bounded measure. So we know that in this case, this quantity here is greater than or equal to just the Fato's lemma for sets, the corollary for of the Fato's lemma for sets. This is actually bigger than or equal to the lim sup of mu ek. Okay, we show that the upper limit of this set of numbers, this sequence of numbers, is equal to 0. And on the other side, I know each one of them is greater than or equal to 0. So what I can say about this limit is that it has to be equal to 0, right? This one has to be equal to 0. Right? That's all because of that this is bigger than or equal to this. That is the corollary of the Fato's lemma for sets. Okay, and it's the limit, so upper limit is equal to 0. And the upper limit must be bigger than or equal to the limit. Actually, if it is greater than or equal to 0 and the upper limit is equal to 0, it just means that the sequence is convergent and the limit is equal to 0. Right? So this is actually just this is just the limit. It has to be the limit because it's just a sequence of numbers. And the upper limit, the sequence of numbers are non-negative, and the upper limit is 0, then they must be convergent and the limit is 0. Okay, and we're done because this limit of this measures is equal to 0 is exactly the definition of convergency measure. Okay, that's the proof. The boundedness for the E is important, just because the corollary for the same Fato's lemma, remember the Fato give you a recall that the lim inf of the set ek is less than or equal to this. Right, this does not require the boundedness of the measure for each ek, but the other one requires that the boundedness of this measure, and then we have the lim sup of ek is bigger than or equal to the lim sup of the measure. This is the one we just used. Okay, and we require this. And that's also why here we also need the boundedness of the set. We should constrain ourselves into a set with a bounded measure. And we can easily construct counterexamples if that's not true. For example, if I define, if this E is unbounded, or this E has unbounded measure, then I can define my fk to be the characteristic function from 0 to k of x. Okay, k is some integer or natural number. And then apparently, I know that fkx will converge to constant function 1, right? Because this will be this fk will be 1 over the interval 0 to k. But when k gets to infinity, I know that well, at least let me just replace this by negative k. Okay, that will convert to constant 1. Right? And that means it's convergent almost everywhere. Actually, it's convergent pointwise. For each point x, we know that for k large enough, it will be 1 there. Okay, so it converges to 1 pointwise everywhere on Rn, on R. But you look at the ek epsilon, it's supposed to be the points where the fk x minus f x, which is 1. This is just constant function 1. It's greater than or equals to epsilon. Let's say the epsilon is 1/2 or 0.1, anything like that. It's between anything between 0 and 1. We realize that this part, say this one, let's just say this 1/2. This will be negative infinity to k, to negative k, and k to positive infinity. And apparently, the measure of this set does not go to 0 because it's always infinity. Right? So that's one counterexample. If we do not have the boundedness, we may not have the pointwise convergence may not yield the convergence in measure, or almost every convergence does not imply a convergence in measure. Okay, so that's one example. I gave another example in the notes. You can take that as an example as well. But this is just to tell you that this boundedness of the measure is necessary. Okay, next, let's show that if we have this nearly uniform convergence or almost uniform convergence, then we can get convergence in measure. Okay. Again, standard setup. Okay, so as I said, if the function sequence of functions fk converge to f almost uniformly, almost uniformly or nearly uniformly, means that for any delta, positive delta, there exists some small set E delta in E such that the measure is less than delta. So you can name whatever small this delta is, just to find some small tiny set E delta with measure less than delta, and the Fk will convert to F uniformly elsewhere outside of E delta. Then we can show that the Fk convert to F in measure. Okay, so if you can still recall what we did in previously is that if you know the if the set E is bounded or has a bounded measure, I should say it has a bounded measure, and the Fk converts to F almost everywhere, then Fk converts to F nearly uniformly in the sense of this. Okay, so the almost everywhere convergence can imply this, and but almost everywhere convergence can also imply the uniform convergence, or the convergence in measure in the previous theorem. But we say that this is supposed to be somehow weaker than almost every convergence, because almost every convergence can imply this, right? That means this is somehow weaker, but we can still use this to show that Fk converges to F in measure. Actually, we don't even require the E to have a bounded measure. Okay? So the almost uniform convergence or nearly uniform convergence is strong enough to give us convergence in measure. Okay, so let's see why this is true. Okay, to show this, recall that if we are going to show the Fk converge to F in measure, our goal is we want to show that for any epsilon, the Ek epsilon can go to 0 as k goes to infinity, where Ek epsilon is the set that we defined earlier, right? That's our goal. Okay, and the goal is, and let's see how to show this. This also means that we need to show for every delta greater than 0, the measure here is less than delta. Sorry, for any epsilon greater than 0 and for any delta greater than 0, there exists some capital K such that this is less than delta for all the little k greater than or equal to the capital K. Right? That's also a coordinate definition for convergence in measure. And that's also what our goal trying to show here. So now for any delta, because of the nearly uniform convergence, we know there exists E delta such that the measure of E delta is less than delta, and the Fk converge to F on E minus E delta. Okay, and that also means that for any epsilon greater than 0, there exists K such that uniform convergence means that Fkx minus Fx will be less than equal to epsilon, or less than epsilon, for all the x on this set, and for all the k greater than equal to capital K. Okay, so that just means the following. Okay, so this is good. Now we're going to rewrite this last line in something that we are more familiar with. So we show that for any epsilon, there exists k such that this will be less than or equal to epsilon for all the k greater than that. So that means the E minus E delta, if X belongs to E minus E delta, if X belongs to E minus E delta, and the K is greater than, then for any K greater than or equal to the capital K, I will have this. Okay, and this just means that X belongs to E minus E delta implies that X is in the intersection of this E, K, well, let me rewrite that so you can see it more clearly, is in the set of points where fkx minus fx is less than epsilon. Okay, well, this set is just the ek epsilon complement, right? Because ek epsilon contains all the points like this one, right? So this is just the ek epsilon complement. So what I'm having here is just a intersection, because it's true for all the little k bigger than or equal to capital K. So it's just intersection of this E little k epsilon complement. Well, if for any x I can show this, that means this E minus E delta, which is just the E delta complement, right? Since the E is its largest set, so it's just E complement, and we know that it's just belong to the intersection of the ek epsilon complement. Well, if we take a complement on both sides, I will have the union, by De Morgan's law, I'll have the union of this, the ek epsilon is a subset of E delta, right? Because this right-hand side is equal to just if we use De Morgan's law, it's just the ek epsilon and then complement. So when I take the complement on both sides, I will just get this. Okay, so this means that, well, from here, the things become easier because of this inclusion. I know that the measure, I don't even need the union of them. I just need one of them. The ek epsilon is going to be less than or equal to the union measure of the union of ek epsilon. Okay, because ek just one of those sets I'm taking union with. Okay, so it must be a subset of that, and we showed that this is a subset of E delta, so their measure is less than or equal to E delta. And I know that this is less than delta for all the k greater than or equal to the capital K. Okay, so what we have shown so far is that for any delta, for any epsilon, we can show that the mu of ek epsilon is less than delta for all the k greater than or equal to k. Oh, sorry, there exists k. So I need to include this. For any delta, any epsilon, I know there exists a k which depends on epsilon delta, such that this measure is less than delta for all this case. Okay, and that is the definition for convergence in measure. Okay, so next we have convergence in measure. Convergence is, as we learned before in analysis, convergence always mostly comes with the concept of Cauchy. Right? We say that a sequence of numbers converge if and only if it's Cauchy. And we're going to have something similar to this for functions. We say that a function, we already talk about the convergence in measure for a sequence of functions. We will always consider a sequence of functions to be Cauchy in measure. And that is the definition I'm going to give now. Suppose I have a sequence of functions defined on E. Again, E is a measurable set. Okay, we see that the sequence of functions is Cauchy measure if for any epsilon, the measure of the set of points where fk and fj are different by at least epsilon is going to 0 as k and j goes to infinity. Okay, we cannot have the ek epsilon as before because we don't know a limit function right now. We don't have a limit function f now. We can only compare two functions in this sequence as we did for Cauchy, right? But this is still similar. Fk minus fj is bigger than epsilon. Okay, so you can also write this in a different way as we define for convergence measure. You can see that for any epsilon greater than 0 and for any delta greater than 0, there exists k such that the measure of the set of points where fkx and fjx are different by at least epsilon is less than delta for all the k and j greater than or equal to capital K. Okay, so that's the equivalent definition. Okay, so this is just the Cauchy version for the convergence, and we would expect something like the sequence is Cauchy in matter if and only if they converge in matter, right? And that is indeed we're trying to show next. Okay, so this is the one side that we're going to show. If a sequence of functions is Cauchy in measure, then they converge to, there will be some function f as finite almost everywhere on E such that fk converges to f in measure. Okay, this is usually the difficult part. Recall that for a sequence of numbers, analysis for a sequence of numbers, if it's a Cauchy sequence, it is if its sequence converges, then it's easy to show that they're Cauchy, right? Just simply by applying the triangle inequality. But if the sequence is Cauchy, to show that it's convergent, it is a little bit more difficult. Okay, and this is the difficult direction that we're going to show here. The idea is similar to the Cauchy sequence of numbers. The idea is that we first try to show that there's a subsequence of fk that they converge to some function in measure. First show there's a subsequence of fk and show that they converge to some function in measure. And then this subsequence, then the next step is to show that this subsequence will drag this entire sequence to that same f. Okay, so that's the two steps that we usually use to prove something like this, to prove that the Cauchy means convergence. Okay. But again, apparently the proof will be much more complicated because we're dealing with functions. But it's not, it's a very interesting process. Let's show that how this is accomplished. Okay, so first we know that all we know right now is that fk is Cauchy measure. So this Cauchy measure is, according to our definition, is just that this the limit of this is going to 0. So for any epsilon, or here, for any epsilon, for any delta, this measure is less than delta for k and j greater than or equal to this k. So this k apparently will depend on the epsilon and delta. Okay? Okay, so this is the thing that we're going to use now. Okay, so first, because this Cauchy measure, we know that for any integer I, for any natural number I, we know there exists some integer ki, index ki, such that the measure of this set is less than this for all the j, l and j greater than or equal to ki. So this is like the epsilon, and this is like the delta, because this is true for any epsilon and delta. So let's just say that I just choose my epsilon and delta to both as this 1 over 2 to the I. Okay, and according to this, we'll have some ki that depends on this I. Right, this I is like the epsilon and the delta. So it will be some ki such that this is true for all the L and J bigger than equal to ki. Okay, that's all because that sequence is Cauchy measure. Okay, so now you can see that for each I we got this ki. Without loss of generality, we just always assume the ki plus 1, ki is increasing in I. So if I got the next ki is ki plus 1 is even smaller than ki, we just choose ki plus 1 to be, I'm saying this is really difficult. Let me say that without loss of generality, we assume that ki plus 1 is bigger than ki. Okay, otherwise, I just set my ki plus 1 to be ki plus 1. The reason is that if this, I can show that this will be true for all the ki, so bigger than ki. So I can just increase it. If it's too small, I just increase it. That's no problem. Okay, and say if this ki plus 1 is smaller than or equal to the ki, then I just change this ki to be this one plus 1, like this one. So that's obviously can be done. Okay, and this ki will be the subsequence I extract from the sequence fk. Okay, then we have obtain a subsequence called fki, and this subsequence is from fk. And now the index is on I, such that let's denote this by this fk. See, we just call this gi for simplicity. I is index. Okay, and according to the the formula above, we can show that, say, I define the set ei to be the set of points where gi minus gi plus 1 is bigger than or equal to 2 to the I. Then we'll realize that the measure of this ei will be less than 1 over 2 to the I. The reason is, if I write this back, you can see this is just a f of ki x. This is just a f of ki plus 1, which is even bigger than ki. But both ki and ki plus 1 are bigger than equal to this ki. So I'm just stating that this is ki, k sub I. This is k sub I plus 1. Okay, and then I know that this f of ki plus 1, this will be the ei. Okay, and this ei has a measure less than 1 over 2 to the I. So the measure of this ei is less than 1 over 2 to the I. Okay, now let's define the set S to be the upper limit of the ei. Okay, and this is nothing but just the intersection for e from 1 to infinity, and then I it will be just this. Okay, note that this this set is a decreasing sequence, right? This set is a decreasing sequence in L, because when we increase L, we're taking the union of fewer sets. So this set is increasing in L, and then this is the limit of that. And because the continuity of measures, we know that the limit measure, we know that the limit is L. So I'm treating this thing here as, say, AL. Okay, and AL is decreasing in L, right? It's a non-increasing set. So the intersection has a limit. It's just a limit of AL. Mm-hmm. Okay, we don't need to worry about the boundedness, because we have seen that the S is lim sup, but the measure of this is, all of them have measure like this. So the starting point has a measure less than 1/2, right? So that's why this must be true. So we can take a look at the measure of S, And according to the definition of S, is just the limit of AL, right? And we know that this is just equal to the limit of L to infinity of AL, and that's just the limit of the union. According to our definition of AL, it's just the union of EI for I from L to infinity. And this apparently is less than or equal to the limit for L equal to infinity. And due to the subadditivity, this is just the I from L to infinity for mu EI. Okay, and remember that the mu EI is has a measure less than or equal to 1/2 to the I. So it's just less than or equal to the sum I from L to infinity 2 to the I. But the sum of this is just 1/2 L minus 1. Right? That's the sum of geometric sequence starting from 1/2 to the L, which is this. And apparently this is equal to 0. Okay, and that means this S has the measure 0. Right? So for any, now we know that S has a measure 0, then for any X, so that's not interest. It's not of interest, right? We don't need to worry about anything happens on S, because S itself just has a measure 0. So now for any X in the S complement, S complement, according to the definition of S, we just need to replace the lim sup by lim inf of EI complement. Okay, so it's just L from 1 to infinity, I is from L to infinity of EI complement. Okay, and this, let me write it out, it's just a set of points where gi x minus gi plus 1x is that's the EI, right? So the complement will be less than 1/2 to the I. So that's the set of S complement. So for every X in this, I know that this is happening. So in other words, I know that I should say in this way. Such that gi x minus gi plus 1x is going to be less than 1/2I for all the I bigger than equal to L. Right? So that means this exists some L such that for all the I greater than equal to L, this is happening. Okay? So that's true. And this also means there exists L. So from this I can derive that because each one of them is less than 1/2 to the I. So when I take the sum of them, it's going to be less than equal to 2 to the I, and that is equal to 1/2 to the L minus 1 as we showed before. Okay, so for any X, we can show that there exists some L such that this series starting from L is less than 1/2 to the L minus 1. So that means this is going to 0, which means this gi of x, considered as sequence of numbers, they converge absolutely at the point x, right? Therefore, the gix as a sequence of numbers converges absolutely at x. Okay, because it converges absolutely, that means they must converge, right? That means I define the function f from E to R or S to R as complement to R. Such that f of x is the limit of gix for r goes to infinity. Okay, because I know that for each point x in S complement, this series exists. That means the gix is converges absolutely. So I just call the limit of this to be the f of x, and that is how I define the function f on every point in S complement. And on S, so I define f on S complement, but on S it can be anything, because S has a measure 0. Because the measure of S equals 0, so it doesn't matter. And by this way, I can get this function f defined on the entire E, because E is just S complement, union of S complement S. So with this two, I can define my function f that is on E to R. Okay. So the key is on this S complement. It is defined as the limit of gi. Okay, so this accomplished the first step. We show that there exists a subsequence of fk that they converge to some point f. Actually, they converge to f pointwise, right? That's because the way we define it. It converges to f almost everywhere because it's converged to f on SC. That's the reason. That's because we define f to be their limit over SC as complement. That's why the GI converges to f almost everywhere, and that's our first step. So the GI converges to f everywhere as complement, and this implies that GI actually converges to f almost everywhere in E. Okay, so that completes the first step. We found a subsequent that converges to some function almost everywhere. Oh, sorry, we haven't completed this first step yet, because we show that it's converged to f almost everywhere. We haven't shown that GI converges to f in measure. Unfortunately, we cannot directly say this, since the previous theorem only says that if I have a sequence of functions converge to f in measure, and this E has a bounded measure, then we can claim that we can also get the convergence in measure. But right now, the E is not necessarily having a bounded measure, so we cannot directly use that theorem. So we have to prove it here. Okay, how to prove this? We realize that the let's look at the difference between my subsequence and this limit function f. Because the gk converges to f absolutely, right? Absolute convergence, as we showed before. So I know that this is going to be less than or equal to the I from 1 to infinity of g I x minus g I plus 1x. This is by triangle inequality. And the fact that the g will convert to f. Okay, convert to f absolutely. So, and we know this side, this is less than equal to, is less than 1 over 2 to the I. Sum of 1 over 2 to the I, but this is just equal to 1 over 2 to the I minus 1. Right? And now let's say where, if I want to show that the GL convert to F in measure, I just need to check this set. I already used the EK before, I just used the FL, epsilon. So this is a collection of points where the GL differs from F by at least the epsilon. And then for any epsilon greater than 0 and the delta greater than 0, there exists L large enough. L is some natural number large enough such that both the 1 over 2 to the L minus 1 is less than both epsilon and delta. Right? Since you choose the for any epsilon and delta, I can choose my L large enough so that this two inequalities hold. And then we can see that the measure of FL epsilon, we know that this set is decreasing, is increasing as epsilon decreases, right? Because this, if epsilon is smaller, then we'll potentially include more points. So I have seen this many times before. This set is increasing as epsilon decreases. Now epsilon is bigger than this, so it decreases to 1 over 2 to the L minus 1. The set will increase. That means the measure will be probably will be increasing. So it's FL for 2 to the L minus 1. Okay, and then this, according to our the fact here, this is less than or equal to this. Okay, so if this one is bigger than epsilon, the sum of this will be bigger than that as well. Okay, but we know that this will be just less than or equal to the measure of the union of these sets. And again, the reason is because if my x is in this set, that means that this is greater than or equal to epsilon. And that means the sum of this is bigger than the epsilon, and that is bigger than, according to the epsilon, this is bigger than this. So it's bigger than or equal to 1 over 2 to the L minus 1. According to the definition of EI we said earlier, let's see where the EI is. That's our EI. Okay, so if the sum is bigger than 1 over 2 to the L, that means at least one of them should be bigger than, so at least one of them should be bigger than 1 over 2 to the I. Because if every one of them is less than 1 over 2 to the I, then the sum of them will be less than this, which is this. But we said that we want this to be bigger than 1 over 2 to the L minus 1. So at least one of them will violate. Well, at least one of them will be bigger than 1 over 2 to the I. Okay, will violate this. That means at least one of them, x will be inside one of those EIs, because the EI contains the points where this is bigger than or equal to 1 over 2 to the I. Okay, so that's why we have this inequality. And then next, this just because of the sub-additivity, we know this is less than or equal to the mu of EI. And according to our the definition of EI, this one has a measure less than 1 over 2 to the I. Okay, and this is just 1 over 2 to the I minus 1. And as we said, we chose this L large enough so that it's less than delta. Okay, so now let's say what do we have? We show that for any epsilon greater than 0 in any delta greater than 0, we can show that there exists L such that the measure of FL of epsilon is less than delta for any L bigger again, I should say that for any L sufficiently large. Because of that, because I can make L even larger, but this one just make this even smaller. Okay, so for any L greater than or equal to this L, I can put this big L here, then this will be true for any L bigger than or equal to this L, and the rest will be fine. Okay, so this shows that according to our definition, for any epsilon and delta, we know we can find this L so that this is less than delta. That means, by definition, that means this GI actually converges to F in measure. Okay, so this completes the first step I just mentioned at the beginning of the proof. We want to find the subsequence of the Fk that they convert to F in measure. Okay, and now the rest is to show that this subsequence will drag the entire sequence to F. Okay, and this will be easy. We can show that for any epsilon greater than 0, let's say the set of points where fkx minus fx, they differ by epsilon. So I want to show that this goes to 0 as k goes to infinity. The measure of this goes to 0 as k goes to infinity. But you know that this by triangle inequality, I can show that this is just less than or equal to kx minus fki greater than or equal to half epsilon union with x or fki x minus fx is bigger than or equal to half epsilon. It's just union of these two. The reason is because fkx minus fx is less than or equal to fkx minus fki plus fki x plus minus fx. Okay, by triangle inequality. So if the left-hand side, again, if the left-hand side is bigger than epsilon, that means the right-hand side, at least one of them, is bigger than or equal to half epsilon. That's why if a point belongs to this, it has to be inside either this or this. Okay, and this ki is the gi we said earlier, and we know that this gi converges to f in measure. So this gi, this fki is like an agent to connect fk and f. I know that this will go to 0 since this fki convert to f in measure, but I also know that this goes to 0 as k and ki goes to infinity because the f is Cauchy in measure. Okay? And this is how we going to show this, the measure of this left-hand side. So the measure of this is less than or equal to the measure of the first. Plus the measure of the second. And I know that both of these two, this will go to 0 as k and I goes to infinity, right? This is because the fk is Cauchy measure, and then this also goes to 0 as I goes to infinity. It's because fki converges to f in measure. Okay, we know this limit. The limit of this measure is 0. Okay, and this in total shows that the fk converges to f in measure. Okay, because this one, for any epsilon, we show that this goes to 0 as k goes to infinity. Okay, this completes the proof. And this showed the one direction, as we said. If the sequence is Cauchy measure, then the sequence exists some function f, so such that the sequence converges to that function in measure. And the other direction is very simple, right? Just using triangulation. If the sequence converges to f in measure, then they must be Cauchy measure. So I will omit that part of the proof. You can do it by yourself.